All right, let's get started very fast. So today it's the week 12 of our course Numerical Analysis for Computer Engineers, and today we are going to continue to learn the methods to find the root of a function, find the zero of a function. So today we are going to learn the Newton-Raphson method. So let me write the title, Newton-Raphson method. It's a very simple method, but by the way, it's a very efficient method to find the root of a function. So we are going to deal a smooth function in our coordinate system. So let me draw the coordinate system first. Let's say this is going to be our x-axis, y-axis, and I'm going to draw a function like I think let's make it black. We have a function like this, and this is fx, and we want to find the root of this function. So it's going to be this point, and also, as you know, we can call this point as zero of this function. And I'm going to start with an initial guess to start to apply the Newton-Raphson method. So let's start with this point, for example. And I'm going to call this initial guess with the variable name x0. All right. So this is our initial guess. All right. So at this point, I'm going to do this. I'm going to draw a slope here. So let's take another color, for example, like this, blue. And I'm going to slope at this point. So I think it should be like, should be something like this. It's a slope. Right? So at one point here, somewhere like this, at some point, our slope is going to intercept with our x-axis. So I'm going to call this point with x1. And then also we have an angle here, and let's call this angle as alpha. All right? So now I can write this tangent of this angle, tangent alpha, like this, right? So tangent alpha, it should be equal to efendim hocam. Sorry for the interruption. So we can write the tangent alpha here, of course, by taking the ratio, by using the ratio between this edge and this edge, right? So this is a point which we have marked with x0. Also have the y coordinates as somewhere like here, and the y coordinate should be equal to f of x0 if we have this curve as fx. So this length should be equal to fx0 then, because we have this line as y equals 0, the x-axis itself. So we have this length as fx0, and also we have this length as, of course, we have this length as x0 minus x1, right? This length. So we can write then the tangent alpha is equal to f of x0 minus 0, the y coordinate at the x-axis, divided by x0 minus x1, like this. And also, we know the slope, the tangent alpha of this slope. We can also use the first derivative of the function itself, right? So, of course, at this point. So instead of the slope, I can also use the first derivative of the function at the point x0, like this. All right, then we can transform this equation into something like f prime, which is the first derivative of the function f at the point x0, and it's going to be equal to f of x0 divided by x0 minus x1. And if we just isolate the value x1 from this equation, then we can get the x1 equals to x0 minus fx divided by f prime x. Of course, the x0 and x0. x0, and also for this one, x0, like this, right? Then we can get the value of x1 by using this equation, and we can just repeat the same thing starting from the x1 this time as an initial guess. So let me draw this dashed line up to the curve and find this point, and this point is going to be equal to f of x1, of course, f of x1, like this. And if we just draw the slope at this point, like this, then we get our x2 here. Then we can use the same equation as x2 equals to x1 minus fx1 divided by f prime x1. So we can just repeat the same thing by using x2 as an initial point now, and then we can draw the slope, and we can get the point x3. So repeating, doing again this method, applying this method again and again to get the next root and the next root and the next point at the x-axis. Finally, we are going to converge to the root of this function. All right, then we get the point which our curve intercepts with the x-axis. So this is going to be our root. This is going to be the zero of this function. So I can use a general formula now. Let's say our general formula for the Newton-Raphson methods, general formula. And it's going to be equal to x, let's say n plus 1 equals to xn minus f of xn divided by f prime xn. All right. So we can apply this method to by starting with an initial guess just with the value x0, and then advance with the next point and next point and then the next point. Finally, we are going to find the root itself. And if we know the analytical expression for the first derivative of the function, then we can just put here the analytical expression and we just substitute the value for xn and we can find the xn plus 1 easily. But if we don't know the analytical expression, or if we cannot find the analytical expression for the first derivative of the f, then we can just apply the method which we have learned from this class, which has the name finite difference approach. So if we use this method, then we can just write the Taylor expansion in the vicinity of the point xn. So let's write it here. So we can just write fxn plus h in the vicinity of xn with a very small value h should be equal to fxn plus h times f prime xn. So we can just get f prime xn from this equation. So if we isolate the f prime xn by using this one, so it should be equal to f xn plus h minus f xn divided by h. All right, then we can substitute the value here, the derivative here, by using this equation. Then we can apply this method, the Newton-Raphson method, for every function if we know just the definition itself. All right, the definition of the function itself. If we don't have to know the analytical expression for the derivative of the function, we can just apply the method and we can find the root after some iterations. Of course, if we use an unlucky guess for the x0, at some point we cannot find the root, or the method cannot converge itself. Efendim. Tamam. Aldığımız yere söyle onu. Onlara söylemene gerek yok. Yok, gerek yok. Olur. Onu aldığın yere söyle, hiç çaktırma. Hı hı. Evet. Tamam. Olur olur. Tamam. Evet. Görüşürüz. Tamam, iyi akşamlar. Sağ ol, görüşürüz. Sağ ol. Of course, if we apply this method again and again, so we have to use an iteration limit. So we have to stop at one point because we can just start with an unlucky initial guess. So the method cannot converge, and then we can say if we reach this iteration limit, then stop immediately. But it's going to be a fixed option, so we cannot say just apply the 10 or 20 or 50 or 100 as the iteration limit. So it sometimes works, but sometimes doesn't work. So I can just apply a tolerance like we did in the bisection method last week. So let's define a tolerance, and let's say if our function, the value at the xn, of course the absolute value, all right, so it can be a plus or minus, it doesn't matter. If it is less than our tolerance, then stop. All right, stop. We should use this condition to stop, to make our method to stop immediately and give us the root which it has found. All right. So I'm going to apply the tolerance method, and also I'm going to use the iteration limit as a safety option. So if you don't have any question now, I'm going to pass to the coding session. So I'm going to implement this method by using Python. So also after this, I'm going to create an animated loop so we can understand what happens really step by step for every iteration. So let's delete this. It's from the last lecture and create again as a new folder. So let's use just name Newton Raphson. All right. So create a PyCharm project at this folder. This is an example file. I'm not going to use it. So close this. And I'm going to create a virtual environment for this one. All right, let's create an empty Python file now. Let's use the same name, Newton Raphson. Now we have it. All right. So at the beginning, of course, I'm going to need to define these two formulas, one for the first derivative to find the first derivative of any function, and also to find the next root of the of this function by using the Newton-Raphson method. So I'm going to create two separate functions to do this, and the first one will be the difference. All right, the difference. So with to find the derivative of a function, I'm going to need this function. So as an input argument, I'm going to get this function as f, and also I'm going to calculate the first derivative at one point, so it should be x, and also I'm going to use an h. So I'm going to use it, which is a very small number, which is a very small value. So let's define this value, and let's say return this function. So it should be f(x) plus h minus h, like this, and let's use parentheses. Sorry, f(x) like this divided by h, right? Then we are done. And let's define another function for this general formula from the Newton-Raphson method, and let's use the name next root. And again, we should get access to the function itself, so f, and also the point, the initial guess, and then the next, and then the next, and then the next root. So I'm going to get the value of x, and also I should call the function diff, which calculates the first derivative of the function from inside this function. So I'm going to need h also in this function. So now we can just implement this formula inside this function. So let's say return x minus f of x. Or we don't need this parentheses like this, f of x with the diff f x and h. All right, then we are done. All right, let's create an example now. I'm going to use a main function, and let's don't write anything here at this moment. And if someone calls this Python file and runs this Python file directly, then I'm going to run the main function. So let's say name equals to the main name, like this. Right. Then, of course, to use this next root function, first I'm going to define an example function. So let's use a polynomial and to create an f x, and it's going to return the, for example, x squared like this minus 4 times x minus 7. Right? So it's going to be a very simple function like this one, which I drew here. So it's going to return this polynomial. I'm going to use it. And in main function, now I can just start with an initial value. Let's use 9 as an initial guess. I want to start this value. And also, I'm going to need an h. So let's use, as we did in the last week, 10 to the minus 6. Like this, and now we can do it. I'm going to create a loop and call again and again the next root function. So let's say for I in range, let's start with 10, and let's print f string. Let's get the iteration number. So let's use this. And then the value of x, I want to see it. X is equal to the next root. It's f, x, and h. So it would call again and again, but if we use it like this, I think we are going to have a problem. But let's see this. Let's see this for a moment. Let's run this file one time and see the output. So this is the answer from the first iteration. So we have started with the initial guess x equals 9, and then immediately it calculates the x1 as with the value 2, so 6.285 something. And then it's not advancing because we don't save the value in the x itself. So let's use the next root function like this, f, x, and h. Then put the x here. Right now. Then it's advancing. All right. It has started with this x1 value. Of course, it just puts the screen with the 0 because the index, as you know, in the Python starts from 0. So it's iteration 1. So we have this value, and then we use this value as the initial guess, and then finds this value. So it converts very fast. I think so. It has just found the 5.31 in the iteration 3. So after this, it doesn't change too much, and I think after this point. So it's iteration 6. After the iteration 6, it doesn't change. All right. So it means so it just finds the same value again and again, again and again. All right. So I think we can just apply the tolerance here. So then our method stops here. Instead of just complete the iterations up to the limit that we have given here. All right. So let's define a tolerance value. So let's say the tolerance, let's use the same value, 10 to the minus 6, like this, and put here something like, before using the tolerance, let's see the, or let's use it, tolerance. I was going to add some condition check here before. So let's say the absolute value. Let's just don't use this one. I'm going to import numpy as np. I'm going to use this one. Of course, we should add numpy into our virtual environment, so do it first. Right, so now we can use it. So let's say np dot absolute value of f of x, and if it is smaller than our tolerance, then break. So it's going to stop our loop immediately. So let's try this. So now we just stop at the iteration 5. I think it was iteration 6. So let's decrease this value up to something like 10 to the minus 10 and try again. No. All right. Can we just... All right, now we get it with 10 to the minus 18. Maybe it just needs to be something like 10 to the minus 12 or 13. I don't know. So we just find the root with these methods. All right. So now I'm going to use another function. Let's change this function to f1. And I'm going to add another function to see another example. Let's define f2. And I'm going to use the polynomial this time 27 times x cubed with the third power of x minus 3 times x plus 1. All right. So let's start with different initial value. Let's just use 5. And the same iteration limit is okay, 10, and use f2 here, and also use f2 here. So let's try again. All right, now we are seeing this. We have this output starting from iteration 1 with an initial value 5. Immediately it just gets the next root as 3.3 something. And we have these roots, but I think we have just used all the iterations up to the limit 10. So we have applied this method 10 times. So I think it's not guaranteed to... I think we don't have the root now. It's just needs to continue. All right. So I'm going to add something into our output. Let's use the fx here like this, and let's say f2x here something. Run again. All right, then we have this output. As you can see, we are not close to 0 at the iteration 10. All right, we have just the value 1. And also in this, for this function, we have some values close to 0, like this one, 0.8 something, 0.6 something, and then it's just increase immediately after this iteration. So it can just, it just it doesn't converge directly to the root, but it can just getting closer or decrease or increase from the x-axis, so it's normal. So I just want to see a better output, so let's add here something like 6.f, so 6 decimal digits. For this, let's use 8f like this, so we can just compare these values better. So now I'm going to increase this iteration limits up to 20 something. Now we have 20 iterations, and it getting closer and then increases again. So it cannot found with 20 iterations. So let's make it 30 and try again like this. And I think we cannot still find the root, but we have these two numbers, which seems equal with this precision, of course, with the 8 decimal digits after the point. So we are very close. We can just change the tolerance here, and I think it's enough. So let's change it to 6 again and run again. So it stops with the iteration 28. All right, it's not 30, because if it is 30, then the iteration 29 must be here. So it's just stops with this tolerance at this point. with the root minus 0.4415 something. Right, so it can just take a lot of iterations, so you should define it dynamical, all right, by using the tolerance. If it is enough for you, then the method should stop immediately after this point. It's just consumes a lot of CPU power or something. So we have these two functions as examples, and now I'm going to create an animated plots to understand what happens actually inside this method step by step. I want to see all the iterations. So we have done it also last week. We did it last week for the bisection method, but in this bisection method, I have just created a class, and then I have used the function animation class from the matplotlib. But this time I'm going to create my class as a child of the function animation class. So actually I'm going to use the inheritance. I think you have already known the concept of the inheritance, so you should be familiar. I'm going to extend the function animation class with my child class. So first, import the libraries that I'm going to need. So import matplotlib. Install it inside my virtual environment. All right. And also, I'm going to import the matplotlib.pyplot as plt as always. And also, I'm going to import the function animation class from the matplotlib.animation like this. All right. So let's create our class. So let's use the name Newton Raphson. And to extend the function animation class, I'm going to use the name inside these parentheses. In Python, we can do it with this way, like this. All right. So let's create our initializer, our constructor. And of course, we are going to get some input arguments. And of course, we are going to need the function itself, the curve, the function of the curve, and also the initial guess x, and also the h, which we are going to use to calculate the first derivative of the function. And also we are going to need the tolerance value and also the iteration limits. I'm going to define this as a separate variable as a safety option, as I have said. So also I'm going to create a plot, so I want it to be fixed. So I don't want the curve moving to the right or left or to top or bottom. So I'm going to fix the scene of the plot. So I'm going to use some variables inside this array, x underscore limits. And also I'm going to control the output to the terminal. So I'm going to use another variable as with the name verbose. And as a default option, it has the value false. And if the user changes this value to true, then I'm going to show the output, show the animated plot, and also I'm going to put some messages to the terminal. All right, some text output. All right, now we have all of these input arguments, and I'm going to store the values inside properties of the class. So let's say self.f will be equal to is going to be equal to func. So self.x will be equal to x, self.h will be equal to h, then tolerance like this, and then the iteration limits like this, and then the x limits. What do we have else? Variables. All right, let's store this value also. Self.variables will be equal to variables, like this. Then to make it to see the animated plot in a separate window, so I'm going to use an option. So let's say matplotlib.use in TK. I'm going to see, I want to use a TK window to see the animated plot. So let's use this option. And also I'm going to control the size of the plot. So let's use RC parameters and format. I'm going to use figure.fig size. And use the size as 4x3. So let's use 12 and 9 like this. And now I'm going to create our figure and also the axis. So self.fig and self.ax, which is going to hold the access to the axis. So it's going to be equal to plt.subplots. And then if this class Newton Raphson is going to be a child of this class function animation, so in the constructor of Newton Raphson, in the initializer of the Newton Raphson, I should also call the initializer of the function animation. So I'm going to get access to the initializer of the function animation by using super method from Python, like this. So I'm going to give the name of the object itself, so the name of the child class, so it's Newton Raphson. And also I'm going to give the self keyword to make it enable to access to this child class. And then the initializer, the init method, like this. Of course, it's going to have some input arguments. The first one should be self.fig. And then I'm going to give a method which our function animation is going to call again and again for every frame. So it's going to be an update method. And also we can use an initializer for the animation. So before completing this list, I'm going to create here two methods. And the first one is going to have the name init animation, like this. And right now I'm not going to write anything, so I just use the pass keyword. And also the another method, the update animation, like this. So it has self as an input argument, and also it should have the frame number. So for every frame, our function animation class is going to call this update animation method again and again, and also it's going to use the frame number as an input argument. So we should get this value by using an input argument. And if you don't need to use the number of the frames, then you can just use an underscore here to throw it away. All right, so I'm going to use, so I should get the value. Right now I just use pass again here, but for the initializer of the animation, I'm not going to use this function actually, but I just define this function, and I think I just define this function as a dummy function. All right, so I'm not going to use it. I leave it with the keyword pass, because when the animation created before drawing the scene, it just calls this function. If you don't use an initializer, an init function like this one, then it's going to call the update animation method immediately. All right, and it just runs the frame number 0 2 times if you don't use an initializer. So it's just going to call the update animation one time with the frame number 0, and then call it again with the frame number 0. But I don't want it to do it like this. All right, so I'm going to use an initializer like this as a dummy method, and I'm going to give the name of this function, but I'm not going to do anything inside this function. So let's first give the update method like this. And then as an init function, I'm going to give the name init underscore animation, of course with the self, like this. And also I'm going to define the interval which defines the time between the frames. So every 500 milliseconds, it's just going to call the next frame again and again, all right? And after this, calling the initializer of the parent class, and then I'm going to show the plot by calling the show method from the PLT, which holds the access to the pyplot from matplotlib. All right, now, and of course, if we create a class like this, I can just use these two functions, diff and next root, inside this class. So I'm going to make them a method of this class. So here, let's define them. Let's def, and I think I don't need to use these input arguments f, x, and h because we just have the access all of the properties of the class. So I just use self here as an input argument. So let's return the same formula, but this time, of course, we are going to use the self keyword. So let's say self.f of self.x plus self.h minus self.f of self.x divided by self.h, like this. All right. So let's define the next root method with a similar way. So def next root. Again, we don't need to use any input arguments. So let's return self.x minus self.f of self.x divided by diff, of course, self-diff. If you don't use a self, then it's going to call this function instead of this method. So be careful. All right, now we can delete these two functions. We no longer need to use them. So we have them inside our class. So now we can just write some Python codes inside our update animation methods. So first I'm going to check the tolerance and also the iteration limits. So let's check them. If, let's say, numpy, the absolute value of self.f of self.x, and if this value less than self.tolerance, or the frame number, which also should be equal to the iteration number, iteration index. So if it is greater than or equal to our self.iteration limit, so if one condition satisfies one of these two conditions satisfies, then we are going to stop. So let's just close the animation itself by using the close method from the PLT. All right. So now for every frame, I'm going to clear the axis. So let's say self.ax clear. And then I'm going to put some information to the title of the animation. So let's use them, self.ax.set title with an f string. So let's put the title Newton Raphson methods. The iteration number is frame. At the x point, self.x, and also I'm going to define the precision here. Let's use the 6 decimal digits. All right, we can put the fx value also. So let's put here. Okay, just continue here. Let's use fx. And it's equal to self.f of self.x, like this, and also use 8 decimal. 8 is not, I think is so long. I think let's use 6 or maybe 4 is enough. All right, like this. So it's going to be our title. So after this, I'm going to create a vector here, including some x values to draw this curve and lines. All right. So let's create an x vector, including some values. So let's say the x underscore points, and it's going to be equal to np dot linear space. So I'm going to create some points starting from 1 point up to 1 point, and between these 2 points I'm going to have this number of points. So I'm going to use the x limits argument for this purpose, which we have inside our constructor, inside our initializer init method. So let's use it. So let's say self.x limits, and it's going to be an array. So I'm going to use the first element as a starting point, and then I'm going to use the second element as a stopping point, as an end. And also I'm going to use the third element as the number of the points between these two values, like this. So we have our x underscore points now as an x vector. So let's fix the limits of the x-axis, and also I'm going to fix the limits of the y-axis, so it should give us a fixed frame inside our plot, so it's not moving to the right, left, or top or bottom. All right, so I'm going to first fix the limits of the x-axis. So let's say self.ax set x lim. So self.x limits 0 start with this value up to self.x limit the second value inside this array. All right, so do a similar thing for the y limits. So let's say y lim. So it should get the values from the function itself to find the limits of the y-axis. So I'm going to use self.f with the same values. So self.x limits 0, and the end should be self.f again with the value, this time self.x limits 1, like this. All right, then let's start with the curve itself. So first I'm going to draw the main curve. So let's use self.ax plots and use the x points, so x underscore points. And with these x points, I'm going to use the f function. So let's say self.f with these values, x points. I'm going to make it broader. So let's use line width with the value 2. And also I'm going to make it red. So let's use color red. All right. And then I'm going to need the x-axis itself to see the intercept points on this line. So I'm going to use a trick to draw a custom x-axis. So let's use it. So self.ax plots with all these x points. And of course, if we want to draw the x points, so the y coordinates at the x-axis, all of them should be 0, right? So let's create 0 for every x point. So let's use it like 4 underscore, because I don't want to use the index here, in x points like this. So for every value in x points vector, the y coordinates should be 0. And let's use line width equals 1 here with the color black, like this. All right. Now I'm going to draw these dashed lines for the roots. All right, start with the initial guess. So the x coordinates should be this point and this point. All right, the two of them have the same x coordinates, which is equal to x0 and x0, and the y coordinates should be 0 for this point and the f of x0 for this point. All right, so I'm going to use this point and this point to draw a line between these 2 points. So let's make it self ax plots, and to give 2 points, I'm going to use square brackets. So let's use self.x and self.x. So both of the x coordinates should be equal to this value. And the first one has the y coordinates as 0. And the second one, the top one, have the f of x as y coordinates. So let's use it like this. All right. So let's use line width 1 again, but the color of this line should be blue. Right. Let's just use some random colors. Now I'm going to put circles for every root. So starting from this initial guess, I'm going to put a circle here on the curve, and also for this one and this one and this one, so we can just see how it converges to the intersection point between the curve and the x-axis. So let's do this. Self.ax plots using self.x, and also of course the f of x here, self.f of self.f of self.x. And to make it circle, I'm going to use marker O, and also to marker size, it can be something like 4 or 5, I think. Let's use 5. And now we should just draw the slope here. All right, only this slope is missing now inside our plot, inside our animation. So I'm going to use 2 lines, 2 points again to draw this line, and the first one should be this point, and this point has the coordinates x0 and f of x0, and using this point itself, the next root. All right, so I'm going to use this next root point with the x coordinate, which is equal to next root, and the y coordinates, of course, it's going to be equal to 0 because it's an intersection point between the slope and the x-axis, not the curve and x-axis. So self.ax plots with 2 points, the x coordinates should be self.x, but the next one with the self.next root, and the y coordinates should be self.f of self.x like this, and the next y coordinate should be 0. Let's use line width 1 again, and the color, maybe we can use green or something. Use green. All right, now we have done with the plot, and to advance the iteration one step further, I'm going to now store the value which is coming from the general formula of the Newton-Raphson method inside to the self.x itself. And when we call this method again, we are going to start with this value as an initial guess. So self.x should be equal to self.next root. And if the user wants to see some messages in the terminal, so it means we have our self.variables as true. So we can check this by using an if like this. And I'm going to print to screen with an f string. Let's say the iteration. Can we use the same one here that we have written? I'm just going to copy this and paste this here. All right, the iteration number is frame, of course. The f of x is the self.f and self.x. So self.x here. All right. So let's use the same precision. Let's use 4 for this one. And also, what was it? 8. 8 is okay. And if we just put here the output messages, let's just call this as a last step after writing the output, right? So it should be consistent between the terminal and the plot. And I think we have written all the required codes. Now we can just, we have our F1, F2, and we have our main function here. Let's delete this and start from scratch. Let's use the initial guess as x equals 9 and h, let's use 10 to the minus 6 like this, and the tolerance, let's use the same value, 10 to the minus 6, and the iteration limit, let's use something like 10 as a starting value. So the x underscore limits, the limits of the plot, let's use start from 2 up to 8 using 100 points. All right, now we can call our class. Let's say Newton Raphson with the function f1, x, h, tolerance, iteration limits, x limits, and x limits, and also the variables which has the default value is false. Let's use 2. I think we are done. Let's try it. All right, we can see our animation. Let's hide these writings for a moment and try it again. And also we have these output messages to our terminal again. And it works, I think, very nice. Let's put a breakpoint inside. For example, let's put it here and run this code in debug mode to see every step one by one. So now we have the initial frame and we have all these values, and we have these x points, we have all these values. All right, that's the next step. We have these values also with these values. All right, the starting point is x equals 9, and the first root x1 is 6.28. It's true, and so the f value, which is equal to 7.36 something, and we have this slope which intercepts with the x-axis here, which is very close to our root which we desire to find. Let's take it to the next step, and now we have the slope as this, so this one should be the next root. So the next one is this. Let's call again, and the next one is this. And I think it's going to stop now after 4 iterations. All right, the 5th one is the final one, so the root here, this value. Let's try this with a different one. So let's add here x equals 5, and I'm going to use the h and tolerance as they are, and the iteration limit should be, I think, 30 for the second function. So let's give the limits as -1 and +1, and 100 points is okay. So let's stop this and run debug mode again. Let's see the console. We have these initial values, and the next step is just draws the curve, and the x now is 5.33, Of course, it's now outside our plot. We can just change the limits of the x, but let's I think we don't all right, we didn't change the f, right? We should get the f2 here like this. So let's try again. Sorry for this with the debug mode. All right, now we have our initial value x equals 5, and we have this value f of x is 3,300 something. Let's take it to the next level with the next iteration. We have this curve now, and still we have a very large value for f of x, and x is equal to 3.33 something. With the iteration 3, it's still very large number, so it's outside the plot. If we just extend the range up to this point, and we can not see this curve anymore, so I'm not going to do this. So let's make it with iteration 3, iteration 4, and now we can see the slope itself. So this value is going to be the next root, so let's make it. All right, now we are close to the root, and root is here, and this here, this curve is going to be a problem, I think. So let's see again. Iteration 6, iteration 7, it's getting closer and closer, and now it's just changed the direction. All right, so with this point the slope turns this way, so it's going to continue with this value. Let's see what happens. And again, it's going to try to converge to the root. And again, it's going to turn to this way. And it just goes to somewhere like 1.06. And again, it's going to try to getting closer to this point. Again. And again, it changed the direction one more time to the right side, and then try to getting closer again. And now it just gets a point like this one, and it just goes all the way up to this part, right? So let's see what happens with this one. So it's outside to the left part of this plot. So the value of x is minus 1.95 something. And let's continue with the iteration number 22. So we can see the slope now. It should it's just try to getting closer to the root from the left side now. All right, it's getting closer. Now it's very close, and now it has catch something like very close to the root, and I think we have found our value with the iteration 28. All right, it's just the final value minus 0.4415 something. So we can remove this breakpoint now and run the file again to see all of the steps at one glance. All right, it works very nice. So I think we have done with this lecture. I don't want to cover any more subjects after this one. So the Newton-Raphson method is the final one. So we have all these numerical derivatives. We have all these numerical root finding methods, bisection and Newton-Raphson. And also we have the error part, of course, at the beginning of the lecture, and of course the conversion to the IEEE 754 notation, the format. And we have all these subjects, and I think we are okay. And next week I'm going to apply a quiz to you. And after this, we are going to just end this lecture, all right? So I'm going to stop the recording now. See you again.